Diesel Engines by A J Wharton. Chapter 1. Engine Types. Marine engines are required to operate safely and reliably in unmanned engine rooms and with extended periods between planned overhauls. They may be expected to operate for considerable periods at low power without ill effects, and to be tolerant of low quality fuels while maintaining very high thermal efficiency. Continuing development and improvement in design are necessary to meet these demands, and new generations of engine models are produced to take advantage of advances in research and experience. Changes in world trade may lead to the emergence of different ship types with special demands upon their power systems. Manufacturers produce a range of cylinder sizes and numbers in each model so that a wide selection of power or other parameters is available. Further sizes are developed when a particular demand becomes evident. Practically all new merchant ships are powered by diesel engines, and some existing large steamships have been re-engined with diesel power to improve their economy and extend their useful life. Marine diesel engines can be divided into two types: large, slow-running, direct-drive engines with limited numbers of cylinders, or medium to high-speed engines driving through reduction gears. Cylinder sizes do not necessarily distinguish between these. Slow-speed engines are available with bores down to 350 mm, while medium-speed engines are produced with bores up to 620 mm. Although there are distinct differences between both types, much of the subject matter in this book is relevant to all engines. When necessary, their characteristics are dealt with separately. Slow-speed engines. This category refers to engines operating at between 55 and 150 revolutions per minute. Large, slow-speed, direct-drive main engines operate exclusively on the two-stroke cycle and are of crosshead construction, which allows complete isolation between the cylinders and the crankcase. They are best able to tolerate low-quality fuels and burn these successfully to obtain the highest thermal efficiencies. Slow piston speed and fewer working parts make them very economical in lubricating oil and give low rates of wear and remarkable reliability. Although there are now few manufacturers producing these engines, they dominate the market, particularly in ocean-going ships. A variety of size and number of cylinders are available to suit all power requirements. In addition to the standard models, they are produced in long-stroke versions with stroke-bore ratio up to 3.8 to 1 and at speeds down to 55 revolutions per minute, allowing the use of large, slow propellers for high efficiency. Short-stroke models cater for ships with limited draft, propeller size or engine room height. Many of the basic engine components are common to all versions. Current models of two-stroke engines are illustrated here together with some older models which are still in operation and have distinctive features of which the student must be aware. Figure 1, on page 2 of the book, shows an RTA 58-84 engine. This operates with uniflow scavenge, using exhaust valves and ported liners to give efficiency while burning heavy fuels. Uncooled turbochargers operate on constant pressure exhaust system, scavenge air being augmented at slow speeds by electrically driven air compressors. The model shown uses bore cooling for all combustion space parts including the piston, cylinder liner and cover, and exhaust valve seats. All these are water-cooled. The pistons obtain their cooling water by telescopic pipes, with all pipes and glands being entirely separate from the crankcase, and this system is separate from that for the jacket cooling. The single forging cylinder cover has 3 uncooled fuel injectors spaced symmetrically around the central exhaust valve, which operate from a distribution block supplied from a valve-timed fuel pump. Hot oil is automatically circulated through the valve bodies while they are not injecting. Variable injection timing is fitted for fuel quality combustion control. Exhaust valves are manufactured in mnemonic alloy for long life, are hydraulically operated and have air springs. The camshaft is gear-driven, and reversing is carried out by servo motors, which retime each fuel pump and starting air cam. Cylinder lubricators are fitted with pressure accumulators to time the oil entering the liners, and the pumps are regulated according to engine power setting. A deep box-type bed plate is used to accommodate the longer cranks of the semi-built crankshaft without unduly increasing overall engine width. To allow fitting the pre-tensioned tie bolts close to the shaft centre, jack bolts are used to secure the main bearing keeps. Figure 2, on page 4 of the book, shows the RTA 84M, which has much in common with the previous engine. It has an increased stroke-bore ratio with lower engine speeds. To allow running gear clearance, the engine has oil-cooled pistons, eliminating the telescopic pipes and glands. The crankshaft bearings have also been changed, and a continuous bottom half crosshead pin bearing has been adopted with a white metal lining. MAN B&W MC engine. Figure 3, on page 5 of the book, shows an engine of this type. A wide number of different sizes are available, together with very long stroke and also short stroke alternatives. All models are able to burn at low quality fuel very efficiently, with very low wear rates. As in previous models, these engines operate with uniflow scavenge, cylinder liners being of simple construction with scavenge ports. Exhaust valves are hydraulically operated by actuating pistons from the camshaft. 3 or 4 uncooled fuel injectors are fitted to each cylinder. They are single-circuit oil circulating valves to maintain temperatures for efficient burning of heavy fuel oil. They are operated from a helix-controlled, cam-operated fuel pump, which incorporates variable injection timing, regulated from the engine governor setting, but also adjustable for fuel quality. The camshaft is driven by 2 roller chains, thereby saving overall weight while allowing the camshaft to be positioned high on the engine, reducing the lengths of hydraulic valve connections and minimizing the effects of elasticity in the pipes. Reversing is carried out by displacing the fuel pump followers. Cylinder liners and covers are bore-cooled by water, while the pistons are oil-cooled, eliminating the need for sophisticated cooling glands or the risk of crankcase contamination. Only 4 piston rings are found necessary. Uncooled turbochargers, powered from a constant pressure exhaust system, are supported with electrically driven compressors for low power operation. The engine bedplate is a rigid construction with cast steel sections in transverse members. The low setting of main bearings limits the necessary width of long-stroke engines. Crankcase bearings include one-piece bottom shells in crossheads and the use of thin shell bearings. The crankshafts may be of semi-built construction or welded in one piece, with considerable saving in weight. MAN B&W KEF engine. Figure 4, on page 6 of the book, shows this engine, which was the forerunner of the later ones. It had many of the present features of modern engines using the uniflow scavenge system with poppet exhaust valves. These were operated by pushrods and rockers and required tappet clearance. They also used helical steel valve springs. The engine shown had turbochargers operating on the pulse system, with groups of 3 or 4 cylinder exhausts connected to each charger. A separate fuel valve cooling system was required when burning heavy fuel. Reversing was carried out by rotating the whole camshaft with respect to the crankshaft, a servo motor being used to alter the timing of both fuel pumps and exhaust valves. These engines gave, and still are giving, good service. The Sulzer R&D engine. The example in Figure 5, on page 7 of the book, is a previous model, but many are still in operation. It illustrates exhaust ports in the liner, which eliminated the need for exhaust valves but limited the engine to loop or cross scavenging. In this engine, a cross-loop system was used. It used constant pressure turbocharging and included arrangements utilising under-piston charging. A long piston skirt was necessary with this system. Cylinder covers were constructed in two concentric parts and had one centrally situated fuel injector which was water-cooled. Reversing required a servo motor to rotate the camshaft to retime fuel pumps and air start valves. The engine cross-section illustrates earlier bed plate designs in which two longitudinal box-like girders were incorporated along each side to give rigidity. Limited throw of the cranks allowed space for these. The Doxford J-type engine, one of the last opposed piston engines produced by that company, many are still operating, and examination questions may include this type of engine, which is seen in Figure 6, which is on page 8 of the book. As a single-acting, opposed piston two-stroke engine, there were two pistons in each cylinder. The lower piston was oil-cooled and was attached to the crankshaft in the normal manner. It uncovered the scavenge ports in the liner. The upper piston was water-cooled and was connected to the crankshaft through side rods and separate crossheads and connecting rods. It uncovered the exhaust ports cut nearer the top of the liner and thus allowed uniflow scavenge without the necessity for exhaust valves. The need for 3 bottom-end bearings for each unit demanded a greater distance between main bearings and a complicated crankshaft design. Despite considerable ingenuity, increasing engine ratings caused severe stress. Being opposed piston engines, tie bolts were unnecessary and bed plates could reflect this. Cylinder valves, including 2 fuel valves, were situated in the liner at the inner end of travel of both pistons. Fuel was operated on the common rail system, with fuel pumps driven from the crankshaft delivering to the common rail while cam-driven timing valves controlled injection. Cams were symmetrical and only the starting air valves required retiming to reverse the engine. Pulse turbocharging was used successfully. Medium and high speed engines. Most of these are designed to operate on the 4-stroke cycle and are of trunk piston construction. They are much lighter and smaller than equivalent slow-speed engines, but require gearing or some other means to reduce the drive speed for ships' propellers. Medium speed generally means between 400 and 1000 RPM. Smaller engines are robust and can be highly rated. Their power to weight and power size ratios makes them particularly attractive where engine room size is limited. They also require less strength built into the ship's supporting structure. Long-stroke versions are produced to give greater fuel economy. Medium-speed engines are widely used in ferry-type vessels and those of limited size. Rapid progress has brought many different models into production and a wide choice exists in size, speed and power. They are well adapted for re-engineering existing ships, fitting well into existing engine space and giving ample power with increased economy. Flexible couplings and torsional vibration dampers are fitted at the couplings between engines and gearbox drives. Plant systems may incorporate a number of similar engines of this type, giving great flexibility for part load operating or maintenance. With controllable pitch propellers, there is no need to fit the more expensive reversible engines. Modern engines can operate successfully on all but the heaviest of fuels with surprisingly low wear rates. Smaller and lighter parts with simpler construction give easier maintenance. Shell bearings are in general use. Engines may operate on either the pulse or constant pressure turbocharged system. As 4-stroke engines, they are self-aspirating at slow speeds. Pulse charging will incorporate pulse converters to reduce the size of exhaust manifolds and improve turbine efficiency. This system may have some advantage where rapid acceleration is required, while constant pressure gives a greater efficiency overall. Turbochargers may require water cooling with the high exhaust temperatures which may be produced. Medium and high-speed engines may be constructed in either inline or V configuration, and many manufacturers supply all but the largest bore models in either form. As the name implies, V engines are constructed with two banks of cylinders arranged at an angle using a common crankcase and bedplate with considerable saving in size and weight. Twice as many cylinders can be accommodated in a given length, although the width of the engine is increased. Due to the increased power from a V engine, however, the crankshaft must be of adequate strength. A variety of methods have been utilised to connect two pistons to each throw of the shaft. Most common is the side-by-side arrangements with two bottom-end bearings. The V formation gives economy in the common space used for exhaust system and turbochargers. Two camshafts are used, but in multi-cylinder engines, starting air valves may only be necessary on one bank of cylinders. The MAN B&W L58-64 engine. Figure 7 on page 10 of the book shows an engine of this type. As the numbers imply, this is one of the larger medium-speed four-stroke engines, with cylinder bore of 580mm, a stroke of 640mm, and inline construction. It can compete directly with equivalent slow-speed engines, operating well on heavy fuels, and designed for ease of maintenance with extended periods between overhaul. This should be an advantage where reduced manning is important. The engine is constructed with a stiff, cast monoblock frame as its main strength member. Long tie bolts pass through this to support the underslung main bearings, which are also braced to the frame by transverse bolts. The cylinder liner has its upper part water-cooled in a separate supporting jacket ring. The piston is of composite design with forged steel crown and aluminium skirt. It is oil-cooled by the shaker method, taking oil from the top of the connecting rod. This rod is jointed near its top end, allowing removal of the piston without the bottom end bearing. The cylinder cover is a nodular iron casting, water-cooled and with passages for exhaust gas and inlet air. 4 valves are fitted, 2 exhaust valves which have stellite deposits and are rotated by the gas stream passing vanes on the spindles. 2 uncooled air inlet valves are fitted with rotor caps, and all 4 valves are fitted in separate cages. A centrally positioned fuel injector is water-cooled and supplied with fuel from a helix-controlled pump, which also has fine-tuning adjustment by use of a rocker lever at the pump cam follower. Constant pressure turbocharging is used, with an uncooled charger allowing high exhaust gas temperatures for waste heat recovery. The Sulzer ZA40S engine. This engine is available in both inline and V models, and can be seen in Figure 8, which is on page 12 of the book. The suffix S indicates that it is a longer stroke development of the standard ZA40 engine, with which many parts are identical. The longer stroke gives improved fuel economy, slightly reduced speed, and allows use of lower grade fuels. There is a large cast frame, and underslung main bearings are supported on studs with transverse bolts also attached to the frame. Cylinder liners are supported on the top surface. Liners and covers are water-cooled by bore cooling, which also circulates the exhaust valve seats. The 2 exhaust valves are of mnemonic alloy and have rotor caps fitted. There are also 2 air inlet valves. All valves are fitted without cages. Composite piston is bore-cooled by oil from the connecting rod. 3 piston rings are fitted in the piston crown and 1 oil control ring at the lower end of the cast iron skirt. A special feature of this engine is its rotating pistons. Each one is continuously rotated by the action of small pawls which engage a ratchet-type ring as they move with the swing of the connecting rod. The rotation ensures that even temperatures are maintained in the piston crown and also assists lubrication of the piston rings. To permit this rotation, a spherical bearing is fitted at the top of the connecting rod. Other bearings are of the thin-walled type. Fuel pumps are of the helix control type with variable injection timing to maintain high maximum combustion pressure at all loads. The turbocharging system uses a single pipe exhaust with pulse converters giving a combination of pulse and constant pressure systems. SEMT Peelstick PC2-6 V engine. This engine is shown in Figure 9, which is on page 13 of the book, and has a fabricated steel main frame. The main bearings are underslung from this with additional bolts to secure them at each side. Cylinder liners are bore-cooled and supported in water jackets. Cylinder covers are cast iron and water-cooled. All air and gas passengers pass through the cover with 2 inlet and 2 exhaust valves fitted per unit. Exhaust valves are in water-cooled cages and have rotor caps. Pistons are of composite construction, 3 compression rings being fitted to the steel crown, with 1 compression and 2 oil control rings at the top of the aluminium skirt. Pistons are oil-cooled, supplied from the connecting rod via a hollow gudgeon pin which is free to rotate within its bearing in the skirt. Connecting rods have thin shell bearings with bottom-end bearing butts angled at 40 degrees to the rod to permit easy passage through the cylinder liner during piston withdrawal. Joint surfaces are toothed to absorb side thrust and shear. Bearings of pairs of units in each V are mounted side by side on a common throw of the crankshaft. A temperature sensor is fitted in each main bearing. The crankshaft is solid forged by the continuous grain process in chrome molybdenum steel. A cam-operated helix-controlled fuel pump supplies fuel to a single, centrally situated water-cooled fuel injector in each unit. Turbocharging is on the pulse system using modular pulse converters, giving benefits of both impulse and constant pressure systems.